our next key approach to interpreting an NMR spectra is going to be based on integration. So integration looks at the size of our NMR peaks. Now you might have noticed when we were talking about chemical shift that I drew these differently sized peaks from our different hydrogens on our NMR spectra. Now, of course, if we go back to our original molecule, so we said, of course, that we had three different groups of hydrogens, again, neglecting this hydrogen over here attached to the oxygen. Each of these groups all had hydrogens that experienced the same chemical environment. They were equivalent hydrogens. So we have two hydrogens that each absorb at the same frequency. So the size of our peak, the intensity, is going to be based on how many atoms are absorbing at that particular frequency. So we have two here, both absorbing at the same frequency. Two here, both absorbing at the same frequency. And now we have three at this position absorbing at the same frequency. The number of hydrogens corresponds to the size of the peak. Right? So in terms of the number of hydrogens, we have 2, 2, and 3 in our three different peaks. TMS, of course, is our standard. The size of that TMS peak depends on just how much TMS you might have added to your sample. So we get this characteristic 2 to 2 to 3 ratio in terms of the size of our peaks because that's the ratio of the number of hydrogen atoms in our original molecule. Now again, this applies to the overall area of our peak, not just the height. That's why we use the term integration. So integration is a technique that's used to measure the area of our peaks. So what we do on an NMR spectrum is we measure the area of each of our peaks. This will give us some random number. So it might be, say, 500 here, 498. These can be relatively arbitrary numbers, but the ratio is always going to be based on the number of hydrogen atoms you have, right? So this then would be around 750 for this peak in that 3 to 2 to 2 ratio, right? So our area, right, is going to be some arbitrary number depending on the concentration of your sample, how long you ran your NMR spectrum in the NMR spectrometer, but the size of the peaks overall, right, the ratio between these areas that you measure should always be based on the numbers of hydrogens in those individual peaks. So the size of our peaks now can tell us something about how many hydrogens we have on our molecule and where those hydrogens are at. So integration is a very important tool for enabling us to identify the numbers of atoms. Now, one of the key things to remember here with integration is that our areas are always relative, right? So this area depends on how much of the molecule you have, what the concentration is in your overall sample, etc. The ratio between hydrogens in the same molecule is always going to be based on the numbers of hydrogens. But only that ratio is absolute, right? The overall areas are relative. To illustrate the relative nature of this integration, let's take a look at another molecule shown here. So in this molecule here, so we have our central carbon, and it's a quaternary carbon attached to 4 other methyl groups, right? Our carbons here with their 3 hydrogens. Now again, just as we saw with TMS, each of these carbons with their groups of hydrogens all see the exact same chemical environment, right? These hydrogens are all attached to a carbon that's attached to this quaternary carbon. They all look exactly the same, right? So these are all equivalent, which means that they'll all absorb at the same frequency or the same chemical shift. And so we just get one large peak. Now this peak, of course, is more de-shielded compared to TMS, because in TMS we have the carbons pulling electron density away from that central silicon. So we get this peak, and now let's say we measure an area. right? So we get some number for our area here, 1960 in this case. Now, what can that tell us about the number of hydrogens? Now, since our area is relative, right, if we have a lot of this molecule, we'll get a large peak if we have a lot of it in our sample. If we have a little bit, we would get a little peak, right? The size of the peak will depend on how much of the molecule we have. Since we only have one group of hydrogens in our sample, we really can't tell how many hydrogens we have at all. We just see one peak, but we have nothing to compare this peak to, right? We don't know if we have the same amount of molecules of our particular compound we're interested in versus TMS. So we can't compare the size to TMS, and we have no other groups of proton peaks to compare this to, right? So we just know that we have only one group of hydrogens with the same chemical environment, but we can't know for sure the exact number of hydrogens. So again, integration doesn't tell us the exact number of hydrogens in our molecule. What it does tell us is the relative numbers of hydrogens in each of our peaks if we have multiple different peaks in our NMR spectrum.